Hello community! Today we talk about how the hell is it possible that an AI tool can design those beautiful images, from text to image, from stable diffusion to whatever. And let me combine this with another question I got. You know that in my last 3 videos I was talking to you about autoencoders. We had some denoising autoencoder, and then the last video was on variational autoencoder. And I showed you in a Python Colab notebook how to code a variational autoencoder. And there were a lot of questions. And I want to answer both questions. How does an AI design images that do not exist? How can it fusion the images together? And what about this variational autoencoder? So here we go. Now, at first, let's remember that this typical vanilla encoder-decoder architecture I showed you in the first video was at the time quite innovative because it also faced a problem. Because if we don't know which values of the latent space correspond to some sensible input that makes sense, so many combinations of the latent values in our latent space will simply result in nonsense. So therefore, the idea was not to operate with the complete latent space, but to have some restrictions on this. To understand how to impose restriction, let's have a look at the simplest form, a linear transformation. So here we go. Imagine we have some raw data points. So we in the input data space, we have some data points x. They have been generated via a linear transformation from some lower dimensional z data. Now, as you can see here, for a linear transformation, x is generated as x equals a times z plus v. Now, z is our lower dimensional data representation, and v is an n-dimensional, independent, identically distributed Gaussian noise. And you might say, yeah, I know this, no? I will always do this when I have raw data in a linear transformation of the latent space. I have this principal component analysis, this PCA algorithm that tries to find an underlying Z representation. And this representation is a lower dimensional representation. So PCA, as our typical linear transformation algorithm, finds a lower dimensional representation. Great, you are familiar with this. Now, next up. Our vanilla autoencoder can learn any latent space it wants if you substitute the linear transformation with a highly complex transformation, but now we have neural networks in the interplay. So it often ends up with memorizing individual data points by placing them in far out sectors of our latent space. So even close to infinity, our algorithm can put our latent data points. So this is, of course, a problem because to compute, we want to have a very close by space. We don't want to tackle problems like infinity. So variational autoencoders, and this is the main idea if you want, overcome these problems of placing our data points somewhere in latent space, overcomes this particular problem by enforcing a probabilistic prior on the latent space. This is the beauty of variational autoencoders. What the hell does it mean? This was the question I received from you. And what is a prior distribution? Okay, so a prior distribution, and you guessed it, is part of a statistical model. So you know now exactly where we are, mathematics, statistics, and should be consistent with the knowledge we have about the underlying scientific problem. So as a scientist or as a physicist, you know, if you look at a physical system and you try to understand it, you try to simulate its behavior, you have some boundary condition and you have some initial condition where this system starts. So you impose some restriction on the possible events that could happen in this system. This is a prior distribution. And yeah, I found the sentence researchers are often experts with the wealth of past experience of this particular system that can be explicitly incorporated into the analysis via a prior distribution. So we impose something that we think that we thought we have discovered of this system, and we say, hey, this is an initial condition I want to impose on this system. This is a prior distribution. And once you have done a few observations of the system, as a physicist, you can recalculate with the new evidence you got, because now you get some time series, you get some further results of the series, and you get the posterior distribution, the after distribution. And there's a very simple idea. You take the prior distribution and some likelihood function of the new evidence, and you got the posterior distribution. Welcome. This was statistics in 5 seconds. Next one. If you are still not familiar with prior distribution in our Latent space, I can tell you a secret. In the most variational autoencoders, this is typical, just a standard Gaussian distribution. So, if you're not familiar with this, we have it here on our right-hand side. You have the two parameters we need, the mean and the variance, so our mu and our sigma square. And as you can see here, for mu 0 and sigma square dot 2, we have the blue distribution curve. For sigma square equal 1, we have the red one. And if you want to shift it a little bit, the mean to -2, we have here the green curve. And you see here, beautiful, our probability distribution. So, given a raw data point in X in our original input space, we also define now the posterior for the Latent space as PZX. Great. We can go on. And now this is the main part. This is the idea why we do all of this. So, this is from Berkeley, beautiful, from ML Berkeley. Have a look at this here. I leave you the HTTPS link. So, our end goal is to compute the posterior for the data, which can be expressed using Bayes' rules. But unfortunately, since we're working with continuous variables, well, hint, in the future we will not be doing this, but for the moment, we're working with continuous variables. Now, the P of X is computationally intractable. So, too complicated. In order to make things able for us, that we can simulate it, that we can compute it in a limited amount of time, we restrict our approximation of the posterior to a specific family of distributions. And it is, of course, the most easiest, the independent Gaussian distribution. And now we call this approximated distribution, where we have limited all our solutions, QZX. And now our goal becomes to minimize the KL divergence. And this was a question I got a lot in my last video. I showed you the code, how to code KL-Div. But what is it? What is the theory behind this? So this is the theory behind it. We have to minimize here a certain divergence. This is a regularization. This is a part of a loss function between the true posterior and the approximated form of the posterior. So, you know this is simply a divergent term. It is not a pure distance term, and it is a distance squared term if you want, but it's too much mathematics. Just that you know, this is why we do it. We want to make this system computable for us. So we impose further restrictions. And this restrictions is simply here that we restrict our approximation of the posterior to a specific family of probability distributions. So now, and last video I showed you the code, and in the code you saw that the loss function for the variational autoencoders had the first term, and I told you that it's just the reconstruction loss. And the second term now is our KL-Div. And this is, it represents a regularization of the posterior. I also found this interpretation that the posterior is being pulled towards the prior by the KL-Div, essentially, and this is it, regularizing the Latent space towards the Gaussian prior. And why we do this? And this has some beautiful effect if you compute it, that it has the effect of keeping the Latent distribution in our Latent space compactly distributed around 0, around a limited space, and we are not heading off too close to infinity No, we are compactly distributed around a very limited region in our latent space. And here we can compute, and we will have further simplifications to our code. So this is the reason why I showed you the code of the KL-Div and why this model is successful, given you have this simplification to, let's call it, reality. But you know what? There's some beauty that also answers the second questions I got from you regarding my video on stable diffusion and this text-to-image AI tools. How is it possible, you ask me, that this thing can create new picture objects that do not exist? In the training data set, there was no way a picture of, I don't know, a horse riding an astronaut, because there was maybe a picture of an astronaut riding a horse or riding a car on the moon, but there was no way, I don't know, from some crazy pictures. And here's now the explanation. Given sufficiently expressive and powerful neural networks between, you remember, our input space and our latent space, and the way back, our variational autoencoder latent space can fit complex data distribution very neatly. The more powerful our neural networks are, the more we can fit some linear transformation like I showed you in the very beginning of this video, but even nonlinear complex data distribution easily done with a neural network. This is the whole reason why we have neural networks. But generally, you can also expect to see a smooth transition between the different types of data point in the latent space. And now this is it. The smooth transition exists within this unobservable hidden space, this latent representation space in a low-dimensional space. This is it. We have smooth transition. And now if you have some crazy wording, this smooth transition enables us exactly in the latent space to create this text-to-image weird pictures. So, for example, and as I showed you, a variational autoencoder trained on an MNIST dataset of our digits from 0 to 9, handwritten digits, you could expect a cluster of the 6th and a separate cluster of the 5th digits. And if you now go between the two clusters, you should get a visualization of the digits that looks like a weird mix of a 5 and a 6. The inter-between of the clusters, there is something because we have smooth transition of the different types of the data points in the latent space. And I think this is the best answer I can give you. Why suddenly we have a picture that is not in the training set in our stable diffusion algorithms? How is the system able to generate those crazy pictures we have never seen before? Well, this is exactly the smooth transition of the different types of the data point in the latent space. And you might say, hey, but this is not about diffusion, this is about variational autoencoder. And you are right, yes. This is, before diffusion started, we had something with autoencoder. And we'll show you in a second what is the next step. But let's come back. Let's come back and summarize it. It's always good to summarize it. So here we go. In my last 3 videos, I showed you that we enforced some structure in the latent space. And in the case of a variational autoencoder, we achieved this by adding the objective that the latent variables outputted by the encoder must approximate a prior distribution. And this was realized by including the Kullback-Leibler divergence, the KL-Div, in the loss function as a second term in the loss function, which measures how much a distribution differs from another probability distribution. So typical statistics, how much two probability distributions differ from one another, this is done with KL-Div. Now, this has also the effect by regularizing this latent space. So these latent variables do not jump from 0 to infinity, but become smooth, more smooth and meaningful for us in our system. And now a sample that we take from this prior distribution, if the system has been trained well on a lot of training data sets, now this results in an image similar to the one with the training data. And now this regularization and this smoothness, suddenly we have created a real generative model. And this is the beauty of the variational autoencoders. Yes, it is an autoencoder, but there's a significant step in this from the pure vanilla autoencoder. Again, if we did not include the regularizer, the KL-Div, in our last function, the encoder would learn to cheat and give each data point of our input space a representation in a different region of the Euclidean space. Because simply the neural network has so much space available, it doesn't need to encode highly efficiently. It just puts the data in all the different corners of this huge infinity space. And of course this is bad. We want to compute this, so we want to have a very efficient code. So this is bad because then two images of the same content, let's say we have a handwritten 2, could end up with very different representations. And we want the latent space or the representation space or the hidden space or whatever you might call it to be meaningful for us. So we penalize this behavior that the algorithm is able to put our data points somewhere in the space. So this has the effect of keeping similar representations, like the handwritten digit 2, close together. Now, topologically close does not make a lot of sense here, but just for you to understand, we have similar representations close together, clusters. And then we train the variational autoencoder using gradient descent to optimize our last function. We have the KL-Div, second term, and this is just standard neural network stuff. Summary finished. And now you said, hey, wait, you said generative. Like in generative adversarial networks? Yes, of course. But generative models, was also a question I received from our viewers, are a specific class of statistical models that are not discriminative models. They contrast completely with them. And the reason is what these models do. So let's have a very close look. Generative models can generate new data instances. This is what happens if you have these text-to-image AI tools. They create new data instances. They create pictures you haven't seen of the data points. On the other hand, discriminative models just have one function. They discriminate between different kinds of data instances. So, what does it mean? A generative model could generate new photos of animals that look like real animals, so a lot of variations of a dog, while a discriminative model can only tell if you have a picture. It is based on the label that this is a dog and this is a cat. So imagine if you're in a linear transformation space, you have a clear line separating all the dog pictures from all the cat pictures. This is typically what PCA does for you. But being able to have a generative model, you kind of compute the whole available space. Let me maybe explain this in a little bit more detail. It's about probabilities. We are still in statistics. So given a set of data instances X and a set of labels Y. So we have a lot of pictures of dogs and cats, X, and a set of labels Y. And we have Y1 is cat and Y2 is dog. Now, the generative model captures the joint probability, or just P of X if there are no labels, and the discriminative model captures the conditional probability. Now, the discriminative model ignores the question of whether a given instance is likely or not. There's nothing about anything else. It just tells you how likely a specific label, dog, is applied to a specific instance, the picture of a dog. So you just have more or less a binary decision, dog, cat, dog. Now with a generative model, it includes the distribution of the whole data itself. And it tells you how likely a given example is. For example, models to predict the next word in a sentence. We remember bird, that bird was trained here on the next, it was masked with a word and the next word and the next sentence and everything, bird. Models that predict the next word in a sequence of words are typically generative models, and they are much simpler than GANs because they can assign a probability to a sequence of words. And this is exactly what we have done with BERT and LL-Proc, and this is what we are doing now in the vision sector. So, beautifully. Let me give you an example here, very easily. Models that predict the next word in a sequence of words are generative models because they can assign a probability to a sequence of words. What does this mean? I got this question. What is it? Now, I've shown you here a sentence. My sentence is, the sun is something. And this is mask. The last word of this sentence of 4 words is mask. And now we have a trained BERT system. And a BERT was trained on word masking task and next sentence prediction task, but we just focus on the first part. And we say, hey, give me all the words that you as a pre-trained BERT model think is, on the English language of course here, is the mask word. And it gives you a probability distribution, the generative model BERT. And it shows you, hey, I have, the first word is dark, but the probability that it is dark is rather low, given that I've been trained on a particular training data set. The second word is narrow, the next one is bright, and the probability increases. Yes, this could be it. But you know, I have one word that has the highest probability in my whole distribution set, and this is shining. So the sentence would be that the answer of BERT is, the sun is shining. Full stop. And then it's other words like beautiful or rising, the sun is down or whatever. But you see, given the probability distribution, the system as a generative system picks what it thinks is the next word in a sequence of words. So, generative models have to model the distribution throughout the whole data space. BERT has to know all the words in the vocabulary it's deducted, because what the hell could be the next word? You have to have the knowledge of all the different words available in your training data set to really find the correct answer to the sentence. And generative models try to model how data are placed throughout the available space, the topological space you're operating in. And this is why generative models are so beautiful, and this is why now there's the context with the particular aspects that I tell you, we have to restrict our available space for the computation. We have to impose some restriction. We have to not allow all possible values or from 0 to infinity, but we limit our available space for computing and simulation tasks. And this is, I think, a very nice example. If you want to learn more, and there's a lot of more mathematics to it, there, and I leave you this link also in the description of this video, there's this beautiful tutorial, what is a variational autoencoder? And just as I showed you the code in my last video about the evidence lower bound, why does it, when you compute and minimize the KL-Div, there is all the mathematics that you need to understand the code, because otherwise you just take the code, whatever it is, and you have no idea what's going on, what you are coding, and how you can optimize the code, how you can manipulate the code, how you can make the next evolution step to the code. So a very nice article if you're interested in mathematics and really dive deep into the mathematical code implementation of variational autoencoders. This is the source you have to go to. And of course, yes, there's an outlook, because my next step with you will be, we will even advance more. We go now to Vector-Quantized Variational Autoencoder, and we impose even a further restriction on the latent space to be faster, to be more efficient. We say, hey, we don't need an absolute continuous space to operate in for our computer simulation. We try to operate on a discrete subspace structure. But of course, we have to do some clever assumption about this vector quantization. And if you remember my video that I told you, hey, physics has a lot to do about the implementation of current AI code. Well, vector quantization. Guess where this is coming from? Of course, physics. If you think about the 19th century, if you think about the electron model, before we had quantum electrodynamics, you had this vectorized quantization coming from physics. And now we apply it here in AI, and it will deliver us some beautiful models. If you're familiar with DAL-E, this was exactly where it was supposed to, based on, this was one of the main building stones. And in my next video, I will show you how we do Vector-Quantized Variational Autoencoder and the beauty it can do. And then, of course, the sky is the limit. And then the next video after this one will be Diffusion. And then we have reached the current state of technology in AI, text-to-image AI tools. I say thank you in this video, and I hope to see you in the next one.